Sudam Surasinghe, who is going to talk about learning transfer operators by kernel density estimation. Please, the stage is yours.
Oh, thank you very much. My name is Sudam Surasinghe, and I want to thank give me this opportunity to present in this conference. Today, I want to talk about learning transfer operator, especially the Frobenius-Perron operator. And in this talk, we are going to introduce kernel density estimation into the this transfer operator sessions. In this talk, first I want to introduce or discuss a little bit about the Frobenius-Perron operator, and then I want to talk about the current existing Ulam-Galerkian method for estimation. Then we will observe that Ulam-Galerkian method is use the histogram density estimation method by using the Bayesian interpretation of the Ulam-Galerkian method. Then in the last part of this talk, I will discuss about the theory of density estimation, and then we will use the kernel density estimation as an approach to the estimating Frobenius-Perron operator. The Frobenius-Perron operator is acting on the densities of initial condition from a dynamical system. For example, if you have a dynamical system F, and instead of acting on a single orbit, we are in the Frobenius-Perron operator is acting on densities. We can, if we have a differentiable map, then we can define Frobenius-Perron operator in the best form or the integral form. Basically, this operator is acting on the densities. For example, we can, in this session, I will use this logistic map example, that is a chaotic map with this parameter 4. But when we have the Frobenius-Perron operator or the density, if we are evolving the densities, we can see that densities are going to a invariance density for any density, initial density we started. So let me give more detail about this logistic map example with this Frobenius-Perron operator. We can use this definition to calculate the act of the Frobenius-Perron operator for any density function rho. We can see this map has two branches, or its inverse is coming from two branches. So that's why we need to calculate this density in these two different branches, and we can add them together. And also we can show that this given density, this rho phi rho x is equal to 1 over phi phi square root x 1 minus x is a fixed point of this operator, or this is a invariant density of this Frobenius-Perron operator, the invariant density. The act is, you can see in this figure, we can start, we can find the, or we can get the random sample of the some initial condition from a uniform distribution, and then we can apply the map. And then again, if you plot the, in this case, I'm plotting the histogram here. If you get the new density after the one iteration of the map, then it is look like this one. The second figure in here, if you do it again, or apply the map again, and then if you plot the densities, then it is looking more like this. And if you do it more times, then eventually it will become it will go to the invariant density function, more look like this. Right. Now how we estimate the Frobenius-Perron operator. The classical method is Ulam-Galerkian method. In that method, we are using a finite topology cover of the our support, and then we are finding a metric approximation for the Frobenius-Perron operator. We can calculate that entries of the matrix by using the element of the bith when xn is the nth iteration of the map, and n+1 is the n+1 iteration of the map. The number of elements coming from nth iteration of bi to n+1 iteration of bj. That is the number of element in that category is divided by the number of element from the bith set. So that is how we use the Ulam-Galerkian method. Now we want to go into the Bayesian interpretation of that method. Then we can realize this Ulam-Galerkian method as a histogram density estimation method. So basically, Frobenius-Perron for the simplicity, I will use the x for the xn between the n iteration of the map and x prime as the n+1 iteration of the map. Basically, in Frobenius-Perron operator, we are estimating the n+1 iteration of the map by using the nth iteration of the density. So we are estimating the probability density of n+1 iteration by using the probability density of the nth iteration. We can actually, if we have the joint density of x and x prime, or the nth iteration and n+1 iteration, this rho x prime is nothing but the marginal density of that joint probability density. This joint probability density also can be interpreted as the conditional probability times the probability rho x. And if now we can compare this this way with the Frobenius-Perron definition, then we can realize this rho x prime x, or this conditional density, is the much similar to the this derivative part. And we can you can find more detail about this interpretation in our paper in 2000. This is basically the kernel of the Frobenius-Perron operator. Another interesting fact I want to mention here is, when we are doing the transfer entropy question, we might need to understand the x prime. X prime is the n+1 iteration of the x value. It might depending on not only the nth iteration of the x, maybe sometimes depending on the another variable y. In that case, the transfer operator is no longer symmetric, it is an asymmetric operator. Similar to the previous one, we can, again, I said, this density x prime given xy using this kernel, and this is actually a kernel of the Frobenius-Perron operator. I'm not going to go more detail about this topic in here, but if you're interested in this geometric interpretation of these things, you can find them in our 2020 paper. Okay, let's move on to the interesting part of this Ulam-Galerkian method interpretation of the Bayesian interpretation as a Bayesian. So previously we saw that this definition actually we can see this is as conditional probability p x prime given bj x prime in bj given that x is coming from bi. So this is basically that pij entry of the matrix which approximate the Frobenius-Perron operator. As we discussed before, we can find this joint density by the number of element in this set, and we can find this probability density as the number of element is in this set. Basically, we can see this as a histogram method. If we know the joint density XX prime, we can calculate we can use the histogram to calculate count this number in each bin, and then again we can use the probability density, the density of the X variable to count the density in each bin. This BI can be represented as the bin of these histograms. Then Pij entry of this matrix is can be calculated using these two calculated values, and that is the just first quantity divided by the second quantity. So now we can realize that Ulam method as a histogram density estimation method. So this is very important observation, because now we can use the standard statistical error analysis to calculate or the better understand the Ulam or the Frobenius-Perron operator. Not only that, we can introduce some other existing statistical density estimation methods, such as kernel density estimation. So that is the important part of that observation. So as I said before, Ulam-Gallachian estimate of the Frobenius-Perron operator is equivalent to this conditional density. Actually, we can estimate that density by using the joint density and the marginal densities, and we can estimate these densities using the histogram estimator. Now, as I discussed before, we can use not only using the histogram estimator, we can use the kernel density estimator or some other density estimators already available in statistical work. So by that important, we can actually control the accuracy of the this operator by controlling the bias, variance, and bandwidth. For example, if you have a small number of bins, k equal 2020, then we have one distribution, and if you have much more bins, then we have another distribution. So how we control this accuracy? So that is the important question now we have. To understand that question, we need to dive into the theory of density estimation. The key issue in any estimator is accuracy versus the data available. In the density estimation, we are using the mean square error to understand the which parameters we need to optimize, how to control them, and so on. So mean square error is the bias square plus the variance. So let me dive right into the histogram method of the theory of density estimation. Histogram method is basically if you have a new X value rather than the data, we are finding which bin is that X value is landing, and then we try to identify the density using that bin. So for any bin, we have a constant density, and if you know where it's landing, then basically we can find that density. So that is the basic idea of this part. In here, I am just presenting the one variant case, but this statistical theory for the multivariant case is also available. We can use that theory in our calculations. But in this talk, I will present the one variant case. So let me go into the bias. Bias is the expected value of our estimator. We can calculate that expected value of this is our estimator. rho nk. This rho is depending on, this estimate is depending on two parameters, n and k is the number of bins, n is the number of samples. We can follow the standard theory of statistic, and then we can find the this bias. Bias is the this minus the actual value. Then we can derive using the standard statistical theory, and we can show that the bias is less than or equal to C1 over K. K is the number of bins. This C1 is actually we need to assume that the densities are smooth functions, and first derivative is less than first derivative is bounded. And with the important information here we have to gather is the bias is a question of balancing the derivative C1 versus a choice of the number of bins. So now the variance, we also need to calculate the variance of our estimator, and we can show that variance is bounded by this quantity, that is just the k times the rho x and rho squared x, and n. In this case, the more bins we are using, the higher variance are suffering. So the bias and variance has the what I want to mean is when k is too large, bias is small because because of this pulse quantity, and while variance is too large because when k's number of bins are getting larger, the variance is getting larger. So we have to find good spot for this k value. So that is the main idea of this mean estimation, mean square estimation. Mean square error, MSE mean square error. We need to balance the bias and the variance, and we need to find the optimal k value. To balance the bias and the variance, we can choose k that minimize the mean square error. Basically, we can minimize the upper bound of this guy. And using the standard statistical theory, we can show that this is equal to optimal k value is equal to n is the number of observation times C1 is depending on the derivative of the rho, and the rho to the power 1 over that. But in practice, we don't have information about our density or the derivative of the density. So basically, we need to use the only idea we can get from here is the number of this is related to number of observation. We should change the number of bins when we have more and more sample size. So for example, here again, I'm choosing that invariant density function for the logistic map, and we try to estimate that logistic map, invariant density of the logistic map using the histogram method. In this case, I'm using 20 bins. This blue line shows the histogram estimation, and this brown line shows the true value. So you can see how error is distributing over here, and main question is how to control that using the this number of bins. In here, I show a few examples what happened with when k is changing for k equal 10 and k equal 20, and when k equal 50. We can see this is the error plot, and actually some of the point exactly touches this line, so that's why the sum of the point it is going more deep down. Error is less, but in overall it is getting better with the k getting increased, and we need to know what is the optimum value. To show that that process, I show here the upper bound, and if I sketch the upper bound of k versus the upper bound of that mean square error, then we can realize the optimum is around 2,503. In that case, we have a much smoother function, much smooth estimation for the this example. Then let me move on to the another estimation method. Rather than using the histogram estimation, we can use any other estimation, but popular and well-known one is a kernel density estimation. I'm here presenting that topic. Kernel density estimation is a non-parametric density estimation, and also it is used the mixing of the similar densities. It uses a kernel. Kernel has few properties. Kernel is has to be symmetric. It is also we can use it also as a normal probability density function, which means when integrate all over the x values, it has to be 1, and k in the endpoint it has to be go to 0. We can use different kernels, but in this process I'm using the Gaussian kernel. If you can see, this is one example with the Gaussian kernel, and if you give for given few points, what this estimation doing is we are adding the densities and normalize the densities by this quantity. For example, we have 1, 2, 3, 4, 5, 6 data points, and in this case we are using the Gaussian densities and add them together. Then we will get this new density estimation, this new density function. All right, so that is the idea. We can use the similar statistical method to estimate the error, find the bias, variance, and then the mean square error. Bias, again, we estimate using the estimator minus expected value of the estimator minus the true value. And if you follow this process, and if you use the Taylor series here, we can finally find the bias is depending on, in this case, delta is the bandwidth. If you go to this process in the Gaussian, it is sort of this variance part, right? So this process or the bias is based on that bandwidth function or the bandwidth of the kernel function. Basically, after realizing this bias, this quantity, we can see that when delta goes to 0, the bias is shrinking at the rate of delta square. So that is the important piece or the take-home message from this piece. The variance, we can do the similar calculation, and after calculate the variance, we can see variance is shrinking at the rate of 1 over delta n square, 1 over delta times n, which means this is a rate of this rate when n goes to infinity and delta goes to 0. As similar to the histogram method, we can see that bias is getting larger when delta is getting larger, and variance is getting larger when delta is getting smaller. So it also has the inverse relationship. So we need to find the good spot for the optimum spot for the delta. So mean square error, to find the optimum value for the mean square error, this we call the asymptotic mean square. we are minimizing this part. To minimizing that part, this first part of the equation, we can get into the optimum delta value. This case, the optimum delta value is depending on these parts. We can't actually, in the practice, we can't find these quantities, but you can see that as some constant. This is depending on 1 over n to the power 1/5. Okay, this is another example of that case when delta is equal to 0.05, how the this estimation and the true value look like. Not like the histogram estimation, kernel density estimation, find a smooth density function. So that is the good news of that. Okay, let me give you a few other examples with the different delta values for this same.
Sorry, time is almost out. So
okay,
I
will finish this in 1 minute. Yeah. For the delta values, different delta values, and this is the optimum delta value. Let me compare this with the histogram method. In histogram, the blue line is histogram method and kernel density estimation value is this one. For the optimum value, we can see the kernel density estimation performing better. The bottom line here is previously, as I discussed, the Ulam method estimate the Frobenius-Perron operator using the histogram density estimate. We observe that is a histogram estimation method. And then now we can use the this new or the other density estimation like kernel density estimation to the same process. That is the big part of that observation. So if I summarize this, Ulam method estimate the action of the Frobenius-Perron operator. Bayesian interpretation of the Ulam-Galerkian method lead us to represent the method as the density estimation for histogram. Hence, Frobenius-Perron operator can be estimated more accurately by other density estimation method. So here we investigate the KDE method. You can use other estimation method as well. Further, we can use standard statistical error analysis to analyze the estimator for the Frobenius-Perron operator. Okay, thank you very much. Here are some references. I will take any questions.
Thank you very much for your talk. Very interesting, right? So we have time for a few brief questions, maybe.
Can I ask a question?
Please.
Why do you define Frobenius-Perron operator on the space L2? Because the space L1 is more natural. For example, if you consider a logistic map, then the invariant density does not belong to the space L2.
Yeah, actually, in practical, there is the definition. We can define this in the L1 norm, and it is in the integral definition, and in practical purposes, most of the time it is in L2. So that's the main reason we are defining in L2 here. And yes, I know that there is an issue with this boundary issue in here, but for this presentation, we are just use the histogram method or the histograms to like demonstrate this idea. Yes, most of the practical cases, and since the Frobenius-Perron operator is the adjoint of the Koopman operator, and this Koopman operator is also in L2 space, so most of the practical examples lives in the L2 norm. So that's the main reason we use the L2 norm here.
But you cannot estimate Frobenius-Perron operator for the logistic map near the invariant density. So you are not able to check the action near invariant density in this way.
I jump in.
Okay.
So yeah, you're absolutely right. It's defined in L1 if you want to go after the invariant density. But this just a statement that looks like Ulam-Galerkin. The Galerkin means like estimating with matrices and thinking of basis functions supported over each like cell of the histogram. Just that statement, the projection statement requires L2. You need the inner product. So the later analysis he does in terms of bias and variance, that doesn't require L2. But also, I'll say that the analysis is just for a one-step action of that operator, as opposed to like the long-term evolution, which is going after invariant density. So that's the main message: is one-step action. You have bounds.
Okay, I have another question, but very technical. You assume that the kernel is defined on the set x square, but in examples it was x simple. Could you look at the definition of the kernel? Where is the definition of the kernel?
There's two kernels. Do you mean the Gaussian kernel, or do you mean the kernel of the Frobenius-Perron operator?
This capital K.
All right.
Yeah, I think I had a small typo there. I think in here.
Oh yeah.
This should be R. Yes. Yeah. I had a typo there. That should be R. Yes.
Okay.
I just realized when I'm talking. Yes. Sorry.
Good catch.
Yeah.
Thank you.
Thank you.
Good job, Sudam.
Right. So